a small moon, which fragmented and broke up into multiple parts.
Granted, because it is always there. However, they will be shocked to hear this earth-shattering revelation by Graham Hancock, that this wonderful satellite is not exactly what we are being told. What has this brilliant researcher discovered about the moon? And why is it so important? Get ready to have your view of the moon seriously challenged by Graham Hancock in this video. The Earth has a single satellite known as the moon. While it has been featured in many poems, stories, and religions, the origin of the moon remains one big mystery. However, fresh evidence presented on Graham Hancock's forum, where people who are like-minded with him, shows that the moon got into its position at a time when humans already populated the Earth. The most popular theories on how the moon came about all have one thing in common, claiming the timing occurred billions of years ago. Consider the fission theory, for example. The fission theory was one of the earliest explanations for the moon's origin. It postulated that the moon was once part of the Earth and was separated from it. This idea was largely based on the moon's orbit and the rotation dynamics of the Earth. George Darwin, a prominent proponent, believed that centrifugal forces from a rapidly spinning young Earth caused a piece of it to separate and form the moon. However, this theory has several shortcomings. For one, the current dynamics of Earth's rotation and the moon's orbit do not align with this hypothesis. Moreover, the distinct compositional differences between the Earth and the moon make it implausible that the moon simply split off from our planet. Another theory, the capture theory, postulates that the moon was formed elsewhere in the solar system and was later captured by Earth's gravitational pull. The primary challenge with this theory is the intricate mechanics required for such a capture. The moon would need a mechanism to decelerate sufficiently to be ensnared by Earth's gravity. The chances of such an event are statistically low. Furthermore, the isotopic similarities between Earth and the moon make it unlikely that the moon originated in a distant part of the solar system. There is also the double planet hypothesis. This theory suggests a simultaneous formation of the Earth and moon as a binary system from the primordial accretion disk of the Sun. However, the moon's smaller iron core and its different density and composition compared to Earth indicate they didn't form from identical material concurrently. However, the most popular is the giant impact hypothesis, or Theia impact. The giant impact hypothesis is the leading theory for the moon's formation and has garnered significant attention and research. It proposes that a Mars-sized body named Theia collided with the proto-Earth approximately 4.5 billion years ago. The aftermath of this colossal impact resulted in a debris cloud that eventually coalesced to form the moon. The theory is popular for several reasons. Isotopic similarity. This compares the isotopic composition of lunar and terrestrial rocks. Both Earth and the moon share strikingly similar isotopic signatures, especially concerning oxygen isotopes. This similarity suggests that the moon's material was derived from the Earth, aligning with the impact scenario. Moon's deficient iron core. The moon's core is actually disproportionately small and lacks the expected iron content if it had formed independently from Earth. This discrepancy can be explained if the moon originated from the mantle material of both Earth and Theia, which would naturally be iron deficient compared to their cores. Computer simulations. Technological advancements have allowed scientists to simulate planetary formation processes. These simulations have shown that an impact of the magnitude and velocity hypothesized for the Theia collision could potentially produce a debris disk around Earth, consistent with the moon's formation. Moon's orbital dynamics. The moon's current trajectory and its gradual recession from Earth support the giant impact hypothesis. The tidal interactions between Earth and the moon suggest that the moon was once much closer to our planet and has been moving away over billions of years. Presence of a northocite. The moon's crust predominantly consists of a northocite, a rock type that crystallizes from molten magma. This composition aligns with the idea that the moon was once in a molten state, a likely scenario following a massive impact. Angular momentum. The combined angular momentum of the Earth-Moon system is consistent with a giant impact event. The dynamics of the collision would have imparted significant angular momentum, explaining the current state of the system. Solar system precedent. The early solar system was a chaotic environment with numerous planetesimals and protoplanets. Collisions were frequent, and the idea of a significant impact event is not only plausible, but also consistent with the formation histories of other celestial bodies. This new look at the formation of the Moon on Graham Hancock's forum, however, presents evidence that points to a capture that occurred quite recently, that is, when people already inhabited Earth. In terms of the chronology and overall capture of the Moon, prehistoric records and unique geological features of the Earth and Moon serve as the pillars of the model's confirmation. The deluge, which appears to have been a cosmic catastrophe that brought higher life on Earth dangerously close to extinction, was brought on by the capture of the Moon. Let us start by looking at unexplained geological features. However, we will be focusing on the Earth rather than the Moon. The prevailing interpretation of Earth's large-scale geology is based on Wegener's theory of plate tectonics. A few anomalies and substructures that plate tectonics cannot explain have been forgotten or gone out. Submarine canyons, which stretch at river mouths as vast underwater waterways, or which are cut into tectonic plates at the shelf brims of continents, are among the unexplained facts. Scientists can rule out that the currents of today have washed or ground them based on the widths and depths of their dimensions. There are even deep-sea tunnels that don't have any connection to any land features or shelf structures. The Aleutian Trench and the South Sandwich Trench are within the category of undersea structures. Both are lengthy, curved, deep-water trenches that are located at a straits shelf edge. Along with the trench formations already mentioned, the South Atlantic anomaly, a vastly significant weakening of the Earth's magnetic field, also exists. Currently, this anomaly is frequently brought up in the context of a potential change in the Earth's magnetic field's pole. In contrast to this presumption, we think and will argue in favor of an explanation that links the magnetic anomaly and the fissured surface of Earth to the same incident. Both conditions can be convincingly described as a simultaneous phenomenon of the Moon's capture. The anomaly in our model corresponds to the course that the proto-moon traveled during its close encounter with Earth. Energy loss during the overflight caused the Moon to slow down, which made it easier to catch. Both bodies were severely damaged by energy loss. The geology, geography, and wildlife of Earth have altered. The planetesimal that collided with the pre-moon must have originated from somewhere. Let's focus on its chemical makeup to pinpoint the area of formation. We expect a body with the Moon's density of 3,340 kilograms per meter cube if we place the Moon's creation in the asteroid belt beyond Mars. Mars, which has a density of 3,930 kilograms per meter cubed, is already alarmingly near to the density of the Moon. A typical asteroid like Vesta has a specific density of 3,420 kilograms per meter cube. From this vantage point, the Earth's Moon's particular density is completely compatible with a theory that places its formation in the solar distance of the asteroid belt. We will now use a quantitative analysis to talk about the capture process, which is the outcome of a very powerful interaction between the two celestial bodies. We will assume that the pre-moon's orbit was elliptical, with an aphelion at 2.6 AU and a perihelion at the Earth's orbital distance. With this orbit, an encounter with Earth would have a difference velocity of 6 kilometers per second. A three-body interaction, that is, Sun, Earth, and pre-moon, impacts a transfer of angular momentum even in the absence of dissipative effects. The encounter can dramatically accelerate or decelerate the lighter body, depending on the relative positions. Calculations show that if the trajectories overlap 20,000 kilometers behind Earth, the orbit of the pre-moon changes. This simulated encounter slows the pre-moon's orbital velocity by 0.67 kilometers per second. This slowing down does not, however, result in its capture in the absence of other energy-dissipating procedures. To extricate the moon from its presumptive orbit would require a kinetic energy of the order of 10 raised to the power of 30 joules. The residual energy is more than enough to modify the moon and Earth geologically, stop the moon's rotation, and shorten the day on Earth by 10 minutes, even at the peak swing-by effect. The braking is firstly aided by the pre-moon's rotation ceasing. The oval shape of the moon's globe is caused by the Earth's gravitational pull during the near encounter. This tidal mountain keeps moving, stopping the moon's rotation while also removing kinetic energy. The deceleration equals 0.19 kilometers per second when the primordial rotation frequency is assumed to be 10 hours. The tidal mountain has been pointing steadily towards Earth ever since the moon's rotation ceased. Later on, as a result, the moon rotates around Earth in a fixed orbit. Along with the lunar body's elongation, gravitational cohesion is being fought. This deformation acts as a secondary source of kinetic energy loss. In the numerical example, a tidal mountain of 1,770 kilometers will rise if the pre-moon approaches Earth at the Roche limit of 18,000 kilometers. The change in potential energy is calculated to determine the work involved by assuming that the lunar mass is divided into two spheres, with a distance that is equal to the moon's diameter. The deceleration with respect to this energy is 1.19 kilometers per s. Now, the moon's geological structure has managed to preserve its deformation. So we see the flat Maria and thin crust of the Earth as we approach. Both are caused by the moon's distortion. At a distance of 20,000 kilometers, we see that the Earth's body is enlarged by 4 kilometers by the gravity of the moon. And when applied to the moon's velocity, the work required to lift anything with an estimated mass of about 6.1017 kilograms will, at best, cause a slowdown of a few meters per second. In comparison to the energies described up to this point, the corresponding energy can be disregarded. There isn't much static in the process, though, and the braking is primarily brought on by the dynamic impacts. Given an average speed of 10 kilometers per second, the passing moon pulls the gigantic tidal mountain behind it in a drag. This movement's enormous amount of energy forms a third energy drain. No mountains are tall enough to stop this water avalanche from crashing on the coast at speeds greater than the speed of sound. According to estimates, the energy present in the rotating surface shell of the Earth's globe is on par with the energy involved in the deformation of the moon's globe. Actually, the land bridge that connects America and Antarctica can't withstand the sky-high water masses and the main waves' crushing impact. The flood rushes over the land bridge, carves out a passage for itself, and spills into a depressed Atlantic basin over the eastern shelf edge of the continent. The Drake Straits geology, with its curved headlands and the undersea channel's flow profile, both serve as clear witnesses to this hyper-tsunami. The fourth energy drains, which are hard to accurately account for, are friction effects and rock breaking, which will undoubtedly have a large braking effect. Now, even though there are opposing views, messages from the past indicate that the moon only became Earth's satellite after there was a human population on the planet. An old map that was created before the deluge provides support for this idea. The Piri Reis map's coastlines of the pre-flood era match up too closely with the South American plate's shelf edge to be a coincidence. The map, which is dated 1513, was certainly created from older, unfortunately lost templates. South America had not yet been discovered in 1513, and there was no knowledge of continental plates or shelf margins either. The facts involving geology and sea biology are supplemented by an argument of an entirely different kind provided by the Piri Reis map. The grotesque distortions found elsewhere contrast with the accurate recreation of other sections of the coast. We believe that the Piri Reis map also depicts terrible destruction in the northern Atlantic, in addition to the shelf edge of South America. The area we now refer to as the Caribbean was once a portion of a continent, or a continental bridge, that linked what is now North and South America. This new hypothesis provides a clear explanation for the disappearance of this geographical mass. The water bulge that was still in the South Atlantic after rolling over South America and eliminating the moon poured back into the empty polar sea in a broad stream. A massive wave that came from the west also flooded the tiny Central America, which may not have even been there yet. It is likely that the collision of the Caribbean plate and Cocos plate caused the Isthmus of Panama to rise above the ocean's surface. Water masses from the Pacific Ocean flowed into the inland sea, known as the Gulf of Mexico and the Caribbean Sea, regardless of whether this impact of isthmus elevation happened. The land bridge was destroyed by the flash flood that the pushed-in water caused to the east. This old shoreline, which spanned from Florida to Venezuela, is suggested by current maps, which show both the mainland and the ocean floor. Only the Caribbean islands are left as remains, rising above the water. This much more easterly shoreline is mirrored on the Piri Reis map. The illustration of the land bridge that previously connected South America with Antarctica serves as a more compelling argument for the accuracy of the Piri Reis map, even if we assume that the Caribbean bridge is indicated with a question mark. The Andes collapsed during the movement of tectonic plates in the south, and a tectonic plate shifted near the Drake Strait. The South American plate caused its rim to be forced into the depths. The ridge of still-active volcano islands to the west led to the formation of the South Sandwich Deep Sea Trench. It is suggested by a contemporary geological map that not only depicts the mainland, but also the profile of the ocean floor, that this previous land bridge is more real than myth. The structure of the ocean floor is completely consistent with our hypothesis that a massive tidal wave tore an ancient land bridge apart. The contour of the seafloor of the strait clearly shows the flow paths of this enormous flood. The two embankments, South America to the north and Antarctica to the south respectively, have the shape of the tidal wave's flow channel, which is also noticeably retained. Massive in size, both banks reach far into the Atlantic Ocean in a distinctive sloped curvature. The Piri Reis map supports this new theory approach. It accurately recreates the shape of the beaches at a time before the deluge, but does not portray the shoreline as it is today. We now feel justified in believing that the Piri Reis map depicts a world from before history. The large island in the midst of the ocean can be taken to be the Atlantis of Plato if we consider the map to be a reliable depiction of a submerged reality. When the passing moon tore up the continent, and this cataclysm caused eastern South America to descend into the ocean, the island was washed away or sank into the sea. All these would probably put the capture of the moon between 40,000 and 13,000 BC, according to one of Graham Hancock's forum users. Globally prevalent myths describe a massive apocalypse. They consequently report on the devastating side effects that came along with the moon's acquisition. More drastic than a flood, the moon's capture altered the world's landscape. Millions of people perished, the surface of the earth was destroyed, and all life was threatened with extinction. The tales of a deluge were forever linked to the event in the collective human memory. There is one other shocking fact that Hancock reveals about the moon. This satellite is still vibrating from an impact that was observed by people on the Earth hundreds of years ago. Hancock presents this fascinating theory in his book, Mars Mystery. This idea is part of a broader perspective that Hancock develops throughout the book, which examines the historical and potential future impacts of celestial bodies on Earth and other planets in our solar system. To understand the magnitude of this claim, it's essential to consider the scale of the moon and the energy required to cause such lasting vibrations. The moon, with a diameter of about 3,474 kilometers, is Earth's only natural satellite. An impact of the magnitude suggested by Hancock would have required an astronomical body of significant size and velocity. The collision would have released an immense amount of energy, causing not only a visible mark on the moon's surface, but also initiating vibrations that could last for centuries. The concept of a celestial body vibrating from an impact might seem strange at first. However, when we consider the immense energy involved in such an event, it becomes more understandable. An impact from a large asteroid or comet would release energy equivalent to millions of nuclear bombs. This energy would cause the solid rock and metal of the moon to behave more like a liquid during the impact, creating waves that ripple through its interior. These waves or vibrations would then be reflected back when they reach the moon's surface. The interference between the incoming and reflected waves could cause the moon to continue vibrating for a very long time. This is similar to how a bell continues ringing for some time after being struck. Hancock's theory also implies that these vibrations could have observable effects. For instance, they might cause slight variations in the moon's gravitational field, which could subtly affect its orbit around Earth. They could also result in seismic activity on the moon's surface, similar to earthquakes on Earth. Moreover, Hancock suggests that these vibrations could have been detected by ancient civilizations on Earth. There are numerous historical accounts and myths from cultures around the world that describe strange phenomena in the sky or significant events related to the moon. One of the primary pieces of evidence Hancock cites is from the Middle East. Ancient texts from this region describe a time when the moon was set on fire or split apart. These descriptions, Hancock posits, could be references to the aftermath of a significant lunar impact. Similarly, some Native American legends speak of a time when the moon shook or moved irregularly. Critics of Hancock's theory often point to the lack of concrete evidence linking ancient observations to specific craters or moonquakes. They argue that the ancient texts and legends Hancock cites are too vague and open to interpretation to be considered reliable evidence. Moreover, the moon's seismic activity can be explained by other factors, such as the gravitational pull of the Earth, without resorting to ancient impacts. However, supporters of Hancock's theory counter that the convergence of accounts from diverse cultures around the world suggests a shared observation of a real event. They argue that while individual accounts might be vague or allegorical, their collective consistency points to a shared experience. Furthermore, they contend that modern science is only beginning to understand the complexities of the moon's seismic activities, and future discoveries might provide more substantial evidence in favor of Hancock's theory. Furthermore, there are also many ancient structures around the world that appear to be aligned with specific lunar events, such as eclipses or certain phases of the moon. These might have been built to track these events and could, therefore, provide indirect evidence of changes in the moon's behavior over time. Also, the moon's scarred surface, riddled with craters, is a testament to its violent past. While many of these craters resulted from impacts that occurred billions of years ago, some are relatively recent. Hancock points to specific large and unweathered craters as potential candidates for the impact site observed by ancient people. The sheer size and freshness of these craters could indicate an impact powerful enough to cause the prolonged vibrations Hancock describes. But how can we ascertain that the moon is still vibrating from this ancient impact? Modern science provides some answers. Seismometers placed on the moon during the Apollo missions have detected moonquakes, seismic activities that occur deep within the moon's interior. While most of these moonquakes are believed to result from tidal forces exerted by Earth, some could be remnants of ancient impacts. Hancock suggests that the continued vibrations from the impact observed by ancient civilizations might still be detectable in the form of these moonquakes.